All right, welcome to my talk. A little bit about me. My name is Robert Peszek. What I can say about myself is probably I'm not the best person to give this talk. I'm not a logician, I'm not a type theorist. I have done quite a few proofs in my life, but then I became a mainstream software developer and I kind of forgot all of it. So this talk is somewhat of a, doesn't have prerequisites, but it uses quite a bit of stuff that if you guys have attended the workshop yesterday about the type level programming in Haskell, that's going to kind of a nice continuation. It kind of continues when the others thing left off. Have you? And can you raise your hand if you've been to the workshop? Cool. Okay. Yes. All right. So a bit of a shameless plug about my employer. I work for Holland Heart Innovation Lab, and we are here in Boulder. We are hosting Haskell meetups more or less every month. We also are growing, and we have actually open positions for Haskell developers. So especially if you are local, please get in touch with us. If you're not local but you have very strong Haskell background, reach to us as well, and at least we will try to talk. So this is a functional programming part of the team. The team is bigger, but there's the three of. So you'll be working with two very smart people and me. All right. Okay. So this pretty busy agenda, pretty good, lots of ground to cover, and I probably will not have time to cover everything. So I should be able to do this stuff, or not. Yeah. So in particular, the super cool type that I may not go to is the decidable type, which it's kind of way improved Boolean. Boolean is kind of a gentleman's agreement that true is true and false is false. Otherwise, it's just two enumeration, right? And decidable is cool because it tells you what is true, what is false, and why is true and why is false. So to actually implement decidable, you need to provide proof for why it's true and contradiction why it's not. So if a type level expression which has maybe like a natural number n, and for some n it's true, for some n it's not, you will need to actually spell it out. So it's extremely precise. I probably won't get there, but it's a super cool thing to actually look at. I will have like very fast motivation for all of this, and these are the types. Well, I'll be using kind of a motivational talk. I want to do it very fast. So my take on this is try to do extremely high level talk, because there's potential that I cannot cover all the details, and try to do a deep dive into very selective areas. So the stuff should look very high level, and it should be kind of quite digestible. And we'll see in a moment. One thing so I let you read the slide, what my plan is. What I want to kind of point out is this line. It's sort of, if you studied dependent types, then this is kind of obvious. If you don't, that's kind of very unobvious. Dependent type programs lift value level expressions to type level. If they do that, they expose quite a bit of stuff about the implementation at the type level. So this concept on which we have built the software industry, that we are hiding our implementation, is kind of compromised. And that creates a little bit of a maintenance headache with proofs, and I'll try to show why and how to deal with it. So this is kind of a nice part of the talk that I want to kind of a little bit focus on. Okay, this is not talk about liquid Haskell. I have one example on the GitHub which uses liquid Haskell. But the idea between liquid Haskell is really nice, and it's nice because you don't need to write any proofs, and if it works, it works. And still allows you to do pretty nice things. So one of my motivational examples is this one, where you're extracting a element from a list, and you can nicely annotate this in a command, and have nice type safety where liquid. So liquid Haskell works this way, very shortly, that you have a kind of a, on top, in addition to GHC compiler, you have another static analysis tool that runs, and it gives you errors. So it kind of does type checking on top of type checking. You don't change anything about your Haskell programs, you just annotations, and make the types very precise. It's not talk about this, I just wanted to point it out. Oh yeah, and please stop me anytime, because I prefer interactive stuff, and yeah. So here is the first kind of example, which is a motivation for why this is really cool. Like having type safety over the size of the list is huge, right? If you're doing any type of linear algebra programming, it is like, it saves you so much work. This is the reason why we do it in Python, right? But this clearly, like, this is something very interesting, that you can do it. That you can say that there's a type, a list of size n, and n is a type level number which defines its type. But this is much deeper. And this is much deeper than just type safety. And I want to sort of show you an example. Anybody has seen Idris' demonstration of kind of interactive programming in Idris? Okay, so some people nod their head yes, some people not. Yeah, let me do that. I just wasted 2 minutes on it. So, so the talk yesterday, there was kind of an overtime where we have introduced, where on the type level programming Haskell workshop, right? Where the vector was, well, this type was introduced. This is vector over there, which was called something like a list n or something like this. I don't, and Thomas implemented append, which I can do it here, but maybe to do something different, I'll go with map. I don't want you to think of it as a map. Don't think of it as anything that is related to functoriality in any way. Just think of it as a type. So let me call it foo, just so it's not a map. Just think of it as a type. So I'm going to ask Idris to implement this for me with a type hole. So this is basically a hole in Idris. And now I have a function and a vector, and I need to construct a vector. I'll ask Idris to case split this on the list argument. So let's split it. So the possibility empty list on an empty list, right? So what's kind of interesting here is that, well, the list size is too much, right? You know what? I'm sorry. This is terrible to watch, and I'll fix it in a moment. Let's do this. Nice. And scroll it down. So there's really one solution for this, right? Even if this was just a list. So let's have Idris fill it for me. And interestingly enough, there's only one solution, recursive solution. You're kind of strongly suggesting that I want to do recursion here, right? The solution space became very limited because the size has to be the same. I cannot like return empty list. So how about I ask Idris and ask it to solve it? And here we go. So the types became so precise that you no longer need to write programs. Kind of cool, right? The same thing is true about append. You can look at this as you can look at this a little bit, like what are the possible. Anybody read? If you guys read theorems for free, there's quite a bit of work of showing that just parametric polymorphism gives you a lot of similar benefits, right? There's the thing called rearrangement of all this. So it's polymorphic. Rearrangement is a polymorphic function that is like from list A to list A. There's quite a few of these. You can just return empty list. And there are very few once you go to a fixed size, because you can only do permutations, but you can't really drop things, right? So the solution space becomes much more restrictive, and that becomes very powerful when you implementing. You have implementation safety, right? So let me minimize this. Good. So this is another motivation. I'll try to go through this very fast. So this type on top is kind of used everywhere. All programming languages have it, and it's kind of terrible, right? There is no way to implement it without throwing exception. There is no total solution for it. If you look at this type as a proposition, that's not the right proposition, right? What it says is that if I have a list of elements of type A and a number of beer cans, I can produce an element of type A, right? I can even correlate integer to have anything to do with the list, right? Type doesn't enforce it. So this is kind of not a good type. But you can fix it, a little bit at least. You can't solve all the problems, but you can add quite a bit of type safety. So the first solution that's kind of common is to do this top line right here, right? This one. It's not a good solution, because as a developer, if I get nothing, what do I do? The solution, probably what I'm going to do is tell the user, hey, I don't know how to program, right? Because this is the situation when I have not dealt with the boundaries, the list size correctly, right? So dependent types fix this nicely in many different ways. A solution that I have on the GitHub is this line. And this is an interesting one, because it uses this type maybe with a type level visibility if it has elements or not. So yeah, I will have to handle the situation where I tell the user that I know how to program, but I have type safety over user not seeing it, which is kind of cool. The super interesting example also is this. So this comes from Idris, and Idris is capable of providing evidence that you are in bounds for the list. Compiler can figure it out, and if it can't figure it out, you can just use it safely. Otherwise, you need to provide evidence. So it's kind of a hybrid approach of kind of dependent type programming. And yeah, go ahead.
So I have a question about the second line with maybe B.
Yeah.
So I understand the constraint, I think, in the maybe B type. But so then, how do you provide? Oh, the user, as you're essentially saying, nobody can call this function if the index will be bigger than the length of the vector. Won't be able to call this. So then, why do you have to call? Why does it have to return that maybe B? Can I put in a constraint?
No. So that accepts any list of size n.
Yeah.
And any natural number m.
And couldn't I constrain in the type level that m has to be smaller than n?
Yeah, so you have two choices, right? You can constrain it in the you can constrain in the argument, or you can constrain in the return type. So this constrains it basically doesn't constrain it, but the return type is smart enough to know what you have done.
I'm sorry, just could you expand a little bit on what a type level maybe is, as opposed to like a value level?
Yeah. Yes. Yeah. Let me try. So yeah. So well, it's clear what. So value level expressions are value level expressions, right? These are the parts from which you build your programs. The bits and pieces you build your programs from. So the value level expressions are, for example, natural number. natural number plus natural number, it's a value level expression. Natural number plus another 1 plus 2 times 3, it's a value level expression. But you can use the type level. Now you have this extra set of abilities you can now do. You can reason about sizes of things, for example, because you have natural numbers. I'm not going to go into the details how this is done, because my focus is really to show how you get in trouble with it. So this is magic. Think of it as this way. So what I'm using is Haskell with a singletons library behind it, and the singletons and bunch of extensions. And the singleton library takes types which are singletons. So there is one value for each type, right? And then uses them to kind of create this type level and value level correlation. So that's some sort of a trickery. A dependency type language like Idris or Agda will do it differently. It will be kind of a semantic ability to just do it inside the language. In Haskell, this doesn't exist currently. There's work being done on this happening. Doesn't make sense? So pragmatically, this is a value level expression. M plus n inside this Boolean. This is a value level expression because that's a natural number. Okay? So that's kind of become more clear probably on the next slide. All right. So we're going to get in trouble. If you look at the bottom line, this is the first trouble you're going to get into. And I'll explain why this is the case. So the goal of this talk is to use proofs to replace uses of unsafe coerce to tell the type checker that these types are really the same. Because if I'm going to achieve type safety by using probably the most dangerous method in Haskell ecosystem, then I probably am not happy about it, right? But there is more to it again. So these three goals, the formal verification, thinking in terms of types are propositions, programs are proofs, and this type precision, solution to this type precision issues are like very, very much intertwined. They come together. You get all of them or none of them, sort of. And this is going to be, all right, so let's do some coding. So let me do. So let's go to the code and let's quickly review. Yeah, that's good. So this Kerry Howard isomorphism, this is probably the most kind of a standard example you can think of. This is kind of a well-known example where you have a proposition which is equivalent to conjunction elimination law in logic, right? So this first is an example of a good proposition and a good proof for it. The program is a proof. But what we do in real life mostly looks like this. I view unsafe write as a semantic rule for imperative exception system, even something like Haskell, right? You have two possibilities, and you encode one of them as an error. You throw exception, right? If you start doing this, that can prove anything. You know, I'm 5 feet tall. Proof, exception, right? It type checks, right? So so this is kind of a bad thing. The next line is pretty much a semantic rule for Java programming language. If it's okay to talk about, if it makes sense even to talk about operational semantics for Java, right? Because what it says is that you know, I have these two cases. One is nothing, and I'm going to encode this nothing as type A. And you don't know that nothing is there.
Well, then I can prove everything. I can be king of the world.
Yes. Yeah, but you know, the point is not to be proving. The problem is to have a software that runs. Okay, so what the goal of this talk is to actually fix it up. So let's just look at this from just and see what can we do better if we introduce dependent types. I'm still learning how to use this. So let's go here. Good. So this is this magic type maybe B, and if you don't know GADTs or GADTs, then don't worry about it. You kind of don't need to know. What you need to know is that this type right here has a Boolean on the type level, and when this type has nothing inside, the Boolean is false. If it has something inside, the Boolean is true. So this shows you this nice linking, right? You have a type level representation of what maybe is. And now this from just becomes completely nice and safe because you do it when it's true. And incidentally, I have the exhaustive pattern match warn incomplete patterns on, and it's not showing me anything wrong, right? Make sense? Any questions? So we're going to play with this type a little bit. I wrote this super sophisticated append using this type. And this append basically says, hey, I'm collecting information. And if I collected something at some point, I need to have something. So if I have two ingredients which collect information, if one of them, I will have in my result, I will have information if either the first one or the second one had something in it. The OR is a type level OR, right? So this is much nicer. This is much nicer than like working with maybe, because maybe if you're implementing this type, you can just say nothing and you're done. It type checks. If I will try to do the same thing here, which I'm going to do now, it's going to tell me, no. And the error actually is not super bad, considering that this is, you know, that's a pretty tough thing to do a good error on it, right? So you have type safety because it knows that types don't match, right? So let's revert this. So then I want to use it. So this is a helper utility because it's so complicated. I have a first known, where the first one is true, the second one is whatever, and I know if I had the first one, so it's there, so I can implement it by using append, right? I also have a second one known, which I'm going to implement now by copying and pasting. Error. Right, a problem in paradise.
Could you show the first now?
Let me sort of make it bigger because I can slide it out. Should be able to slide it out, yes. Now, there's enough symmetry in the whole solution that I can trick it and say flip up it. But I think this is just cheating. This is not right? I'm not going to do that. There's something fundamentally not that I don't understand here.
So is there a way of putting in a proof
Yeah.
of the commutative order?
Yes, that's the next step. That's the point. So what's happening, we'll explain what's happening in a moment, but what's happening really, it doesn't know how to unify these types, right? It expects, from here it expects to have B, this is B, and this is true, and doesn't know that B or true is B. It just doesn't know it.
It knows that's true and B is true.
Yeah. Yes, exactly. Why doesn't know? And this is another thing which creates this thing to be a little bit brittle, and I'm going to explain it too in the next slide. But the point is this: that so what's happening? Next slide explains really what happens, because you can ask a question: what the hell is OR on the type level? Where it came from? This is very similar in any dependency type language. If you've done it in Idris, you have very similar issues, and the Idris will do it kind of internally. I'm going to explain in a moment, but let me revert it so I'm compiling, because I hate not to be compiling.
Sorry, just a quick notation question. So I see some of the type level Bools, like the first true and the first known, that doesn't have a tick in front of it.
Yeah, because I'm lazy. For clarity, you should always use tick.
Okay.
But if you don't need to be clear, like I don't, then you don't. So there are probably a few cases where a type checker has problem and some ambiguity, and then you won't compile unless you have a tick. But it will be very rare.
Oh, the tick says definitely type level.
It means type level, yes, type level value constructor, right? The true is a type is a value constructor for Boolean. Tick true is a type level version of it. All right. So let's do this. Yeah. So there's a problem in Paradise, and basically what's happening is that type checker doesn't know rules of Boolean algebra or any other algebra for what matters, because it just doesn't know. And frankly, why would it? And we just gave it the definition of plus. How would it know that it has a abelian property? There's like no reason for it. You could try to build it into the language, but then you start building who knows what else into the language. So there's a solution for it, and I'm going to explain it. I'm going to use it a lot. So this is this type level propositional equality, which works this way, that you can construct it only by giving the same type. So there's a trick to it. And I'm going to talk a little bit more about it. So here are examples, right? 5 is 5. These are type level 5s. But 4 is not 5. Interestingly enough, 2 plus 3 is the same as 3 plus 2, but n plus m is not the same as m plus n, because why? An idea why? Why it can unify 2 plus 3 and 3 plus 2, it cannot unify where these are type variables? Well, no. I think, so what's happening is like, right, there is a normal reduction happening in functional language, right? Like functional languages separate evaluation from execution. There is this lambda calculus happening, right, underneath the hood, and there are reduction rules. So 2 plus 3 reduces to 5, and 3 plus 2 reduces to 5. So they're the same. But once they're variables, there's no way to reduce them. They're variables, right? It becomes a proposition that they are equal. And we don't have a proposition. So the way I look at this, if you see REFL, it stands for reflexivity. If you see REFL, you kind of asking compiler, do you know that? So this is right. So this basically says, hey, do you know that? And said, no. Do you know this? Yeah. Right? So you can think of this as this definition of equality as basically, hey, things will be equal if normal reduction reduces them to the same value. And you kind of work off of it. The same thing for Booleans. It's kind of pretty clear. I'll just skip over the slide. So this is it. So interestingly enough, there's one semantic change to the language, which is spelled out here. That pattern matching on the variable of this type produces proof that these types are actually equal. In Haskell, this thing is just equality of types. So the Haskell will just unify them, and compiler will just unify them nicely. And then everything else for you to work with comes as a library. So you have a library of combinators to write proofs. And this is some of the interesting combinators that I kind of have a crying face here because it's so hard to sometimes remember that you need to, you need to have correct left and right side when you're doing arguments. I never had to do that writing real proofs, like, real proofs. Whatever that means. Yeah. So let's maybe not dwell too much into it and do some proofs.
Can you say a word about the unexpected one?
Yeah, sure. Yes. So this is somewhat unexpected, right? Because if you look at the apply one, it's like saying, hey, I have two functions that are equal, and I like this one, right? Like the apply one, and I have two elements that are equal. Then the values have to be equal. That's sort of right. It's saying the function cannot split stuff apart, cannot split one argument. This is weird because it sort of looks like, hey, I have a function equality, and I'm inferring the arguments were equal, and that's not always true, right? Because functions can collapse things. But these are not really functions, these are type constructors.
I think it's related to the fact that like when you do certain type values, Haskell says you can't have a non-injective type value. So if you think about the math,
yes.
it's basically saying Haskell shows type.
But I think it's sort of a thing that comes with a nominally typed language, in which you have like new types, right? And basically you cannot, language tries to keep things apart at all cost. It doesn't have a structural equality applied anywhere. So things never collapse. They don't collapse because they have the same representation in memory. There are different as types. So that's what it is. It's sort of specific to how nominally typed languages work. All right, so let's do some proofs now. Let's take this thing apart and prove it, and do the second known and first known, and let's talk about why, how to do that. All right. So to test what we've done before is we are testing the first equality worked, the first known worked, because compiler just knows this. I just asked it, hey, do you know it? Yes, I do. But it turns out that it doesn't know the reverse. So if I do this, it's going to, oh gosh, sorry. If I do this, it's going to complain. In the same way as before, actually, because it's exactly the same thing that's happening. Yeah. Typically, when you write proofs, you actually go for something a little bit more sophisticated, and you go like this. Let me provide you an evidence what B is, and then, but it still doesn't work. So the reason why this is the case is how OR was implemented. So here's the implementation of Haskell OR. It case splits on the first argument, and then no matter what B is, it knows what the value is. If you implemented it differently, if you case split it on the second argument, the first theorem would fail, the second one would be okay. So you have this now weird thing that implementation details change how your compilation works. It's crazy, right? It's like, I don't want to go there almost. But it's not so bad, actually. And right. So let's do the proof. And actually pretty clear how to prove it. Let me go back to the slides. Let me go quickly back to the slides. So these are the booleans. it sort of knows where you have a normalized value level expression what to do, right? So how would you prove it? Well, how would you prove this generic case? You just case split it on one of them and have it, or on both of them even, and you then have just bunch of value level expressions to deal with. You know what the values are, and for all of them, it's going to know because because there are value level expressions that are already normalized. That's it, right? So the proof kind of is super simple. So that's the proof. That's the proof of this kind of a lemma. And this is the proof that this actually commutes. And I don't like this proof. And the question is, why does it even work? Can we have let's have a quick look and ask yourself the question: why the hell does it even work? Because if you look at the types, this is not exactly what you want, right? Right? You know that here. You know that B1 is true. So in this position, you know that you have a true or something equals something or true. And I'm just saying, hey, I'm going to use T1, and T1 doesn't say it. Doesn't have a B here on this side, right? It doesn't say this. So how does it know? It knows because it implicitly again applies the first thing. It applies it implicitly. And this implicit stuff is a bit dangerous.
Could you go for that process one more time?
For this?
Yeah. So just to be clear, this compiles, right?
Yes.
And this provides the proof for the
Correct.
compiler. Okay.
Correct. But it's not very stable proof, because if you change the implementation of OR, the proof is going to be, you'll be working on the proof.
Can you show that? How that would be?
Well, it will be hard for me because I would have to go implement different OR, leave it through singletons. Maybe you can do it offline, because it's like 5-minute exercise.
Okay.
Make sense? So basically, what the idea here is to write proofs which are robust. And the best thing to do is, again, case split it. Because it's bulletproof. You're not relying on any implicit definitional equalities that come from the implementation. Does it make sense? What I'm saying. Does it make sense? Right? I mean, what happens is this provides you a type level definition, definitional inequalities that true or B is always true. It's definitional. Compiler knows about this. But you're relying on it. If you change implementation, different definitional information is going to be pushed up to compiler, and everything you relied on is going to be messed up. So what you want to be is more explicit of what you're actually using. Unfortunately, there's no good linting mechanism which will tell you, hey, by the way, this type of proof is dangerous. And I think it would be cool if there was one. Okay, so now with this knowledge, we can now do the trick and implement second known. And the way we do it is using the proposition. The second one is probably cooler, that all commutes. I can just use append. So this is the semantic rule of the language. If compiler sees expression that type checks to the equality of between A and B, then it can assume that A and B is the same and can unify. Does it make sense? Well, now I need to start running. I mean, because I have a bunch of stuff to cover. But no, but does it make sense? So this is basically bringing evidence. You can think of it this way. I'm bringing evidence of this theorem, and now having this evidence, I can just use the append right on. And I don't like the way this is implemented. And so what I don't like is the first, so this is an opinionated statement, right? The first known would just compile if I would just use append. But I say in general cases where things are unstable, don't do that. Spell out exactly why, and don't rely on the definitional stuff that comes from the implementation. Make sense? All right. Have I lost you? So we kind of covered this. I'm just going to skip over the slide and go to the next one. So with natural numbers, you go through recursion. And the same way as we are proving for Booleans, you end up getting recursive proofs. And let me quickly show you how they look like.
Is this stuff on GitHub?
Yes, absolutely. Yeah, and it's in the Slack channel for the room. You have a link to that. So here's a proof that plus commutes for natural numbers, and maybe so you do basically recursion, because you're helping out you're helping out the reduction process of the language. You recurse down until it gets to value level expressions, and it's pretty much standard how functional programming works, right? The issue here is performance, and I want to a little bit address it. Because, well, you're paying, at least in your course, in this case, I choose quadratic, for proving stuff at runtime. I mean, it's crazy, right? So there are ways around it, and maybe I will not describe all of them. One of them is create a combinator which makes proof fast, which basically, under the hood, uses a safe course, but uses in a safe way. And the other one is use rewrite rules. And you can do rewrite rules correctly and incorrectly. Because since you're rewriting this to unsafe course anyway, if you do it wrong, your program is going to crash and burn in real time. So you don't want this, right? But the description is basically create a type, something like believe me, which you implement it with this, and then the type constraint prevents you from doing it wrong. If I would do it like quite often it's suggested, this way. Then if I would just forget about this R here, this thing still type checks and it will crash during runtime. because it's not right, because it's things are, because you are safely coercing things which are no longer the same. So this is in the GitHub. If you want to, you can run it. You can see actually the proofs not being invoked. If you do it in GHCI, then there's a bit of a problem, because you should invoke something like test. Because if you evaluate this in GHCI, it's going to not apply the rule until after the first evaluation. Just kind of an interesting nuance of how GHCI works. And there's another thing. When you proofs, you want to sort of know that they are total, because I can just do like let X in X and prove anything, right? So use quick check to verify your totality, because the language doesn't do it, and then you kind of nice and golden, and it's kind of pretty meaningful, I think.
What is quick check doing?
So quick check, what this quick check does, it verifies that the thing terminates, because I'm using proofs, right? So you want to verify that the proof terminates, because if you have non-terminating proof, you can really prove anything. Yeah, you can prove by using infinite recursion, which kind of doesn't go anywhere, right? You can have non-terminating recursion, for example, or throw exception or something, use error function and prove it, right? So that checks that your proofs are decent, at least.
It's not really proof, it's more like
Yeah, it's, but it's strong evidence. The proof will be to use Idris or Agda, a language which actually checks totality.
Okay, yeah.
So, yeah.
No, I thought like you did some magic.
No, there is no magic. Here, there's just no magic. All right. And in real life, so all of this work I have done was based on a natural number I have defined myself. And on vector that I have defined myself. But in real life, you probably will be working on GHC typlets. And what the GHC typlets have is they pretty much have no implementation. All of it is hidden. Nothing gets exposed to type level. And you kind of messed up. Meaning that you don't have definitional equalities to start proving anything. So, yeah. So to prove typlets, to do proofs on typlets, because, well, you have the same errors when you're working with typlets and more. This is the trick. You can create this type, which kind of converts between GHC type level natural and something that looks like a piano natural, right? It does look like it, right? And now this guy can be used the same way as we've done it in the previous proofs. The only thing is that you need to sort of bootstrap it. You need to give it some information, something that's equivalent to you saying, how did I define plus? Because the plus for typlets, there is no definition. It's under the hood. So you need to say that, hey, I'm defining plus by doing what? 0 plus n is n. 0 for the successor is 0, sorry, 5 minutes, yes. Plus for the successor is adding it to the element and taking successor on all of it, right? And this gives you definitional equalities, which are reintroduced here by doing basically, doing believe me, because you have nothing else. And now you can bootstrap everything the same way. All right, I don't think I'll have time to do the decidability, which is probably the coolest part of all of this. But maybe it's best actually if I let you ask questions more for the last 5 minutes.
Could you give an executive summary of what you...
Yeah, absolutely. And maybe I should go back to slides because I actually have it. Okay, so this is the decidability slide. Sorry, David Hilbert, I'm not going to talk about it. There is, so this is basically a bunch of resources. So basically, you have this huge potential of extreme type safety, right? We have very precise types because you have a type level expressions that you use to constrain things. Like you know that vector of size n plus vectors of size m has to, when appended, create vector of size n plus m. That's a powerful constraint that makes your program's type checker work much harder and give you positive results. But with this type precision comes the cost, because type checker doesn't know how to unify certain types and is going to say, well, these types are different and you're telling me they're the same. So what you do is you provide you provide hints to the type checker, yes, they are equal. And you do it in a rigorous way by writing proofs using this interesting type, which is the propositional equality type. Make sense? In addition to that, you get in trouble because these proofs don't maintain very well if you don't do them well. So try to do them well. Basically, try to think of the maintenance aspect. What happens if the implementation changes? And you understand what I'm saying? What means definitional equality, right? It comes from the definition of the implementation. Does it make sense? What definitional means?
Yes.
Right. It comes from the case split that you used in implementing. This case split is something equals something. These become equalities that compiler can use. But if you case split elsewhere, you have different, right? You bootstrap from different definitional the propositions, right? So this is it. And I think this is pretty fascinating because you can really do cool programming, but you get in trouble because it doesn't type check. So you do proofs and it type checks. Yeah, any questions?
Yeah, so like practical question, just like I do find it fascinating type level programming, but at the same time, the industry is just horrible, and we keep on redoing things. The clients get their mind changed and all that. So I wonder, like, how much effort you have to put extra to write additional proofs, and then how it becomes frustrating maybe when the next week you have to implement stuff.
No, so I think what's going to happen when Haskell becomes independently typed, the proofs are going to come with basic libraries. Okay. One of the things you want to do, you want to keep the proofs very close to implementations because otherwise the maintenance it's impossible, right? So you have a vector library. This vector library is going to come with its own proofs as a library. And this becomes very stable because once they change something, they change the proofs at the same time, right? So it's not so much hardship. Also, a lot of it will be completely hidden from you because like basic combinators like vector append don't need it. A vector reverse needs this, but it's internalized. So if you have a already vector reverse, you don't need to write your own, right?
So, and it also means that I can spend a little bit more time on proofs themselves, but then I don't really have to write tests because I have proofs that the function is doing what it's supposed to be doing, right?
Well, it does because your types are much more precise, right? So your types become more of a specification for what needs to happen, right? But there's a limit to how far you can go. This type precision is very effective in doing things like, very rigorous things like maybe network protocols. But you have a client which says, if I do this, throw me an apple. If I do this, throw me a banana. Then creating specifications for it is hard, right?
So this is more for like library authors than it is for...
At this moment, and there is definitely research of trying to extend this, but at this moment it works better for something which is formally specified, so we can write formal specification for it already, right? If there's no formal specification, then the hardship is to create one, and then how do you do that, right? Working with, go ahead.
Could you in a nutshell say like how that understandability becomes a problem when writing those proofs? Because I can only imagine that there will be some statements which are correct but are not true.
Well, this gives you extremely precise types because you kind of need to exactly know when that type makes sense and when it doesn't, right? So, for example, it gives you. So, for example, if you want to write something like a less, use less between numbers. You can very easily kind of mess it up because there's no type safety there. Yeah. But you can have a less on the type level, and you can provide that it's decidable. So less, which takes two numbers and returns Boolean, now takes two numbers and returns a decidable statement that they are less, right? And now this becomes very precise. You cannot mess it up. There's no way you can implement it wrong. Becomes very rigorous proposition. It's like, and I can show you an example, maybe offline, of how this works. So that's definitely very, very, very nice. It becomes almost too precise. Well, yes and no. So like in a dependent type language, you will not be implementing things twice. You just can use value level implementations on the type level because the language does it, right? And what singletons do is they use template Haskell to write a bunch of boilerplate. So it's kind of automated. And it gives you more or less, not exactly equivalent, but close to equivalent functionality. So this OR I have not implemented in two places. OR was just given to me for free from singletons. The plus between numbers, I was not implemented in two places. Singletons kind of down the left. Does it make sense?